Thank you, DK, and this is actually my second time at talking at MUG. I think I was here for MUG 2 and now MUG 4. And I must say it's always a pleasure working with guys at OSU and with DK. It's sort of one of the major things we did together, if I remember right, was in the organisation of one of those supercomputers a few years back. And I tell you, it got quite frustrating working with DK. And that's because my initials are DK. His initials are DK, well actually he's not DK. And so we would get a lot of email coming in, right, addressed to DK, can you do this, can you do that? And what I learned was that all the good emails that were coming in were directed towards that DK, and all the bad ones were directed towards me. So it's a great pleasure being here. And to set the story straight, Gillard, I did ask you for more time, but I asked you for more time to prepare my slides, not to present them. So I'm talking about a project that is underway at PNNL, and it is actually in stark contrast to Carl's software-oriented project, in that we're looking at new technologies, test beds for new technologies, and test beds that maybe we can go out and buy today, or buy very close to today, as well as the impact of possible future technologies on future systems. And I'm going to say a little bit more about that. First of all, though, I'll start off by giving you a little bit of an overview of systems and resources at PNNL. Pacific Northwest is a national lab, DOE national lab in Washington State. It's part of the Office of Science complex. Sister labs being Argonne, Oak Ridge, and Berkeley, Lawrence Berkeley. We've got a couple of big large-scale systems at PNNL. Cascade was installed 2-3 years back now, and it's about to go through an upgrade over the next 12 months. On installation, I think it was number 17 on the list, 3.4 petaflop, mic-based with InfiniBand. And quite a bit of memory per node, which is sort of unusual for a lot of the systems. A lot of the computational chemistry type codes that we do run on the system require a lot of memory. We've got internal clusters. Constants I list there is institutional computing. Institutional computing is open to all members of staff to get some time on it. Heavily competed, but it's more as a sort of try and see type system before we try and get time on some of the leadership class facilities elsewhere. We also have on-ramp systems that are supposed to reflect getting into some of those other large-scale systems. So, for instance, in that category, we've got cloud test beds, Hadoop cluster, KNL, older NVIDIA GPUs, and test beds, which is where I'm sitting inside CENATE, is where we put instrumented type systems. Tend to be smaller scale. CPERL, Data Vortex, I'll mention a little bit. A DGX1, the 8-socket Pascal system from NVIDIA, HMC, hybrid memory from Micron, Contuto, the NVRAM coming out of IBM, and also other network test beds. We use MVAPICH as well, and it's very interesting to note that we do have a large internal user base. And when you go around and talk to these guys, it's almost unanimous that MVAPICH is the library of choice. It really is, and a number of things that are quoted for that reason is easy to use, it's easy to install, it's higher performing, and it's got leading edge optimizations inside it. It's very well recognized for that. And it both goes from the research group that I'm in, but both into the production environment as well. So I must applaud you guys that are heavily involved in working on MVAPICH and developing it. Keep going for sure. Also interested in many of the other tools that you're adding into the MVAPICH at the moment. The InfiniBand network monitor, the energy monitor also. CENATE, Center for Advanced Technology Evaluation. This is a center that was recently set up at PNNL by the Office of Science, and its remit is to explore the impact of future technology, both in terms of doing some empirical studies, testing and measurement on available systems, as well as looking at predictive testbeds. Testbeds that we may well set up in terms of a notional type system that may be possible, but may be fed by expectations of future technologies. We saw graphs from Gillard earlier about future systems. Maybe those numbers will come true, maybe they won't, but they'll certainly guide what those systems will be capable of doing. Inside CENATE, we've got 4 major thrusts. One dealing with instrumentation of systems, and we don't just measure performance, we're also interested in power, reliability, thermal effects also. We put in place test beds. We put in place an evaluation strategy that stems from low-level benchmarks to applications as well, and I'll touch upon that a little bit. And importantly, we couple that with modeling and simulation. So what we do measure from the smaller scale test beds, we use as a basis point for modeling and simulation, seeing how those test beds could well scale in size, how the technology components could well scale over time as well. A lot of this came about from experience that we had working inside a DARPA program. A DARPA program that was there to achieve 75 gigaflops per watt for general purpose computing systems. That was called Perfect, and if I thought hard I could remember what the acronym meant, but let's just keep it up, Perfect. It was set up 3 or 4 years ago when state-of-the-art systems were achieving 2 or 3 gigaflops per watt. But inside that program, they were actually touching upon many different aspects, ranging from circuit design, architectural design, system software, and also application development too. And the bullseye in the middle was trying to achieve 75 gigaflops per watt. In actual fact, in that program, there were all sorts of different aspects that were being proposed to be applied into achieving that goal. Very few projects, there were 17 in total, very few projects were actually aimed at end-to-end solutions. Some projects were tackling individual aspects inside that space, from the devices to the applications. Our role was actually what they called a test and validation activity. Our role was to see if each one of these projects could actually live up to the promises they were making. From the results of their research, from the early numbers they were producing, could they actually be applied into providing a solution? So we had piecemeal elements of what was going on inside this space, and we had to assess that as a full system solution. It's still an open challenge, but it's something that has certainly directed us into looking at how to analyze future systems in the DOE space. And so in CENATE, what we're going from is really from looking at early concepts, and I'll mention a few that we got active at the moment, how those concepts can put into design of certain systems down the road, maybe take on board some of the prototypes, test beds in this case, and then those prototypes may well lead to large-scale deployment in future systems. I'm not talking about here in particular Summit or Sierra. Those are the two systems you mentioned right earlier. I'm not talking about those. I'm talking about systems that may well happen in parallel or beyond those. Those have already got their roadmaps. They've already got a timeline, etc. So what we're looking at is seeing how things could develop beyond that. Predictive modeling can be used throughout that sort of timeline, right? And test beds certainly get deployed in the prototype stage, and also coming onto the test bed stage, we can look at measurement evaluation. We deal with subsystems around processing, memory, network, and also touching up on storage and I/O. This is actually quite a reasonably sized project that we expect to be long-lived as well. Looking at emerging paradigms beyond what we see in mainstream multi-core and accelerated systems, looking at approximate computing. Also, we got guys looking at quantum computing, topological quantum computing, as well as some research on materials, and those are all actually in-house at PNNL. Brain-inspired processing structures, neuromorphic type things, and also superconductive systems. Also interesting to note that the current quantum system works at 15 millikelvin, if I remember right, and the superconductive systems work at a much higher temperature of 4 degrees Kelvin. Also looking at different workloads, from the classical scientific type workloads, classed as numeric down here, into the machine learning space. And in fact, one of our key members in that space grew up at OSU, Abhinav Vishnu, and was also part of the MVAPICH team while he did his PhD here. Data analytics and graph analytics, and you also see there's some emphasis on that in some of the test beds we've got. I'm gonna speed up a little bit because I'm going to run out of time actually. The measurement lab, we've got various resources in place. One we put in place through internal investment was what we call the Advanced Measurement Lab. And inside that, we've actually got workbenches where we're not afraid to take the lid off some of the systems that we get. We take them to pieces, we start poking them, adding probes, physical probes, soldering, shining, well, when they allow us, or when we're brave enough, flipping heat sinks off things and shining thermal cameras at them, and measuring sort of different effects that are going on inside that. In fact, one of the latest deliverables we had was a 4-node data vortex system. As soon as it went through acceptance testing, we took the system to pieces and started soldering all sorts of power instrumentation inside that. They were a little bit unhappy when they saw that, and we had to take them out for a beer afterwards to calm them down, I think. Their nice, new, shiny system that was just installed and working. Some of the instrumentation does go into some of our scalability clusters. CPERL is one of them. It's a 64-node system. It includes AMD Fusion type processors. It includes older Ivy Bridge, some Haswell, and all of those things are instrumented for power and thermal using a 21-channel device from Penguin Computing working at 1 kilohertz. So sampling power and thermal activities at 1 kilohertz. If I remember right, there's 13 power sensors and 8 thermal sensors in each node. It gives us some very good information about what is going on inside when we run applications on that. The instrumentation is a key aspect on this, one at which that we're going to try and start doing so many idiosyncratic type instrumentation activities, one-offs if you want, and try and come up with best practices that certainly will be open and visible to everybody. Taking a multi-tier approach, for instance, in power instrumentation, from looking at external power through to the internal power. You may be using the RAPL type sensors, and also using high-speed power instrumentation as needed. The metrics of interest here are not just power, I mentioned thermal, reliability, performance as well, and there's a great interplay between those things. Something that we could talk about at length. And of course, when we look at instrumentation, when we look at even at one of these dimensions, this is power, you look at power at different temporal resolutions, and you see very different effects. You sample too little, and you could assume that the peak power consumption here is actually considerably less than the peak power consumption when you go down to a finer temporal resolution. So you've got to be careful when you look at and observe these systems. On the evaluation side, because we're dealing with a lot of very different technologies, we're actually coming up with a very different strategy for looking at the applications. We're not assuming that we're going to be running turnkey benchmark code. And this is actually inspired by another part of a DARPA program in which it was problem orientated, in which we specify what the problem was that we wanted to try and solve, the input data associated with that problem, and also what the output should look like. We might give reference implementation code, but we certainly different solutions could well be given and run on different systems. An example there is image classification, where you've got a set of images as input, and you've got labels labeling what is in that image as output. And so however you come and process that data, it's completely open. And in fact, we've got a benchmark suite. We talked about this at IPDPS this year, and that is already open with about 20 different problem specifications in there. Of course, when we look at time and power, two of the primary things, we can analyze it in different ways and look at different systems in terms of who achieves the minimum energy inside that. I wanted to talk about minimum time to solution, I guess, on the y-axis, and you got the minimum power usage, also the highest amount of time taken, and the curve of minimum energy, and a couple of points hit that. And there are different people interested in different aspects. A lot of people discount the power argument, but certainly in the embedded space, power is a premium, and one that may well become more and more important down the road. Sample workloads that we touch upon, as I say, they come from the numeric space. Some of those type of applications will probably be very familiar to you, many MPI based. And then we've also got machine learning, data analytics. We've got a whole group of people working in HPDA, an acronym that was picked up actually in the National Computing Strategic Initiative, and HPDA standing for High Performance Data Analytics, mainly dealing with graphs. Test beds, and this is where we get onto discussing networks a little bit, but our test beds range from looking at computing, looking at memory, networks and storage, as well as looking at novel processing paradigm too. And also emerging technologies that may well be more at the device level. Many of the tools that we've got in place are there that can actually model new devices, new technology nodes in terms of technology shrinkage. We're very much initially focusing up here in terms of near to market type systems and applying this down the road as some of these technologies become more realistic. I should have added carbon nanotubes down there. That's mighty interesting also. One particular network testbed that we've already got in place is something called the data vortex. It's a little bit different. It's got a little different topology that you may be used to. And it's also there to deal with smaller messages. Messages of size 64-bit. The data vortex, the topology is shown here. Consider these as a set of source nodes, and data flows through the network from the source node to the destination nodes on the inside. And data basically flows through to the middle. When it sees contention at any one of these nodes, the data will pass around a ring and try and propagate in as it goes around the ring. It was born actually 18 years ago in one of the petascale computing projects within HTMT, for those who've got a longer memory, and it was aimed at being a pure optical network at the time. This is an electronic implementation. As I say, a FLIT in this is 128 bits, 64-bit data payload, which is very good for graph processing. Associated with this is the switch, but also is the VIC, the Vortex Interface Controller. That has got a little bit of memory inside it, but it's FPGA based, and it's there for preparing packages going out and doing a lot of message or data rearrangement on the fly, and certainly this is very programmable. Being FPGA based, you could actually do just about anything with it if you want. But from my sort of sense of programmability, I'm much more application focused. It's got a very low level API for using it for doing one-sided sends and receives. Something that I'd love to overcome, something I'd love to have a MVAPICH interface to it, an API interface. Another network testbed that we're putting in place is here to try and emulate a larger scale system using a smaller footprint, compute node footprint. So consider a system that's realized in n nodes, and we might have like a factor of 4 ports coming out of each node, and we can emulate a larger scale network from that limited compute footprint, and go further using modeling and simulation to look at larger scale systems. This is a testbed that we're actively pursuing and putting in place right now, and one in which we're working with Mellanox in collaboration in putting in place. Another aspect of this which is interesting in my view is that if you imagine a normal type system topology with InfiniBand, we're exploring how we can integrate in there an optical circuit switch. An optical circuit switch that allows us to dynamically reconfigure the system. And when I talk to program managers or facilities guys, I say, well, this will be able to recable your system in 50 milliseconds. Now that's got various amounts of challenges. The optical circuit switch, the current instantiation of the technology usually comes in about 320 port switches, and it's MEMS based, which has 2 arrays of rotating mirrors. It allows you to have an optical data path between any input to any output. So you can set up the mirrors to allow any node to talk to any other node, one at a time. That's the principle of OCS. By incorporating it into the network between the nodes and the switches means that you can effectively configure the switches or the nodes and have any connectivity that you want with the available IB switches that you've got. It allows you to do topology research. It caught the attention of DDN storage as well, and so we're looking at impact on storage systems also. I got a chart here that shows a couple of possibilities of how that OCS could fit into such a system. It could be to the side, and it's great for persistent, long-lived communication between communicating partners. Or it could sit in the middle between the nodes and the IB switches. Here, I'm running out of time here. One key element also in this centre is modelling and simulation. Topology research and exploring different topologies very interesting to us, has been for a long time, and some well-known topologies are there, but there's also various other ones being explored within what they call path forward, design forward, fast forward of DOE as well, that we're tracking and following. Some of the predictive work we also looked upon within CENATE, looking at silicon photonic networks. There's a couple of good prospects out there. One from Oracle that have a 64-site macro chip with an all-to-all optical network in there, and also a technology, another, if you want, an optical circuit switch from IBM, in which this is the IBM system here, in which you may have a vast number of optical planes, allowing that all-to-all communication and allowing anybody to talk to anybody else, 256 planes against 64 nodes. And this particular study was really looking at the energy efficiency. If we compare and track expected power consumption within, say, an IB network compared to the expected power consumption, I should say energy consumption, of the optical circuit switch. In actual fact, we do see some advantages, very much application dependent. Anything below 100% here shows an advantage of the optical silicon photonic type network. Because these are built on assumptions that working with IBM or Oracle, in this case on the silicon photonic side, and working with Mellanox that didn't give us anything for future projections of power, but we made reasonable guesses on what we would expect of that. Coming to the end of that, hopefully I've given you a bit of an overview of what we're doing inside this test centre. Many of these facilities we are there to make available to people, and in actual fact we'd love to work with people, especially in making some of these systems more usable. The data Baltics is one of the cases in point, but also the other thing is exploring such an integration of OCS with InfiniBand and seeing there's challenges in that, and seeing how we can overcome some of those challenges. So here I'm going to stop there.
Okay, so let's thank